Hello, this is Lab 5 for Physics 2212. This lab is based on Faraday's law. Introduction. The purpose of the experiment is to collect observational data of a magnet falling through a conductive tube of an aluminum foil and model the magnet/tube interaction computationally and compare the computational predictions with the observed data. This is all done to ultimately help us understand Faraday's law and to better understand it by seeing it in action. Some concepts we'll be using for this lab include the Biot-Savart law, the Faraday's law, and Newton's law. The final results can be seen as follows. The actual experiment resulted in 1.25 seconds, while the computational model gave us 1.14 seconds. Data collected and some initial measurements. The length of the tube was 0.3 meters, the width was 0.060 meters, the inner radius was 0.0244 meters, the radius was 0.03 meters. The value of mu calculated from lab 3 was 2.05 amps per meter squared. The mass of the magnet was 0.025 kilograms, and the average time came up to be 1.25 seconds after 5 trials. Now coming to the computational model. In step 1, we input all of our initial measurements, which is the length, width, inner radius, and radius. The mass of the magnet was 0.025 kilograms, and the mu mag was re-entered for 4.7. This is because the value from lab 3 was inaccurate. In step 2, I created a function to calculate the magnetic field of the bar magnet. This uses the formula from the initial slides. And in step 3, I created a formula to calculate the change in magnetic flux for the bar magnet. In step 4, we calculated the current induced in the ring, and in step 5 and 6, we calculated the magnetic field in each of the rings. In step 7, I computed the gravitational force on the magnet. In step 7, part 2, I calculated the net force acting on the magnet. This is the sum of the gravitational and magnetic force. In step 8, we applied Newton's second law to calculate the bar magnet's velocity and new position. The results of the computational model. On the left is a velocity time graph. This was found using the new mu value considered, which was 4.7. This closely mimics the ideal velocity time graph. On the right is the velocity time graph from the old mu value, 2.05, calculated during lab 3. As you can see, this does not result in the ideal velocity time graph, and therefore 2.05 is an inaccurate value. Hence, we had to refactor this and sort of estimate a new value for mu, which was 4.7, as it resulted in an ideal velocity time graph, or the one that was expected. On the very right is an image of the following bar magnet. The conclusion of this experiment. From this lab/experiment, we have learned to study Faraday's law, both through computational and experimental methods that allow us to better understand what is going on. As a subproduct of this experiment, we also learned more about magnetic flux and induced current. The time value for the actual experiment was 1.25 seconds, whereas a computational model came up to 1.15 seconds. Some of the errors in this lab, unfortunately due to some human errors and perhaps some other errors, the value of mu found in lab 3 was not accurate, and we had to roughly find a new value for mu using the computational method as well as estimation. This was done to match the mu value in order to produce an ideal velocity time graph. Answering the discussion questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? According to Ohm's law, which is V is equal to IR, this would increase the value of the current immensely as the resistivity of the tube approaches 0, and it would take even longer for the magnet to make it through the tube if the experiment was done again using the same procedures. What if holes or slots were cut into the tube? How would this affect the rings? And how would it affect the currents induced in the rings? If holes or slots were cut into the tube, the model would have less rings, hence a smaller n value, and would result in a reduction in the induced current alongside reduced magnetic force. This would ultimately cause the time taken for the magnet to fall through the tube in the experiment to decrease.